A physician wants to develop criteria for determining whether a patient's pulse rate is atypical, and she wants to determine whether there are significant differences between males and females, using the sample rates below. So we have pulse rates for males and pulse rates for females. Construct a 95% confidence interval for the mean pulse rate for males, round to 2 decimal places. Construct a 95% confidence interval for the mean pulse rate for females, round to 2 decimal places. Using these results, is it possible that the population mean pulse rate for males and females is the same? This is the first time we're using raw data to construct a confidence interval, and there's a different function on the calculator for using raw data. It makes the process really easy. So we're going to start with males, and we're going to put the data in a calculator list. And while we're at it, we might as well put the data for females in the calculator, in a different calculator list. So we're going to second stat. Oops, sorry, it's just stat. It's just stat, not second stat. Okay, so press stat, enter on edit. I'm going to put the data values in L1 and L2. So I'm going to clear L1, clear L2. L1, I'll put the pulse rates for males. 96, 56, 64, 84, 76, 88, 56, 76, 72, 72. So 10 males. And for females, 104, 84, 104, 88, 96, 68, 96, 88, 96, 124. Okay, so that's the first step in handling raw data when dealing with confidence intervals. Okay, the first question you'll want to answer is whether or not to use the normal distribution or the t-distribution, because at this point we've seen solving confidence interval questions in two different ways. One where we are using the normal distribution, the other one where we use the t-distribution and we have to refer to the t-distribution chart. When do you use one and when do you use the other? Well, you use the normal distribution if you have the population standard deviation, and you use the t-distribution when you don't have the population standard deviation and you have the sample standard deviation instead. In this problem, you don't have either, but you do have the ability to get the sample standard deviation, because this is sample data. And we have at our disposal calculator tools to help us arrive at sample standard deviations if we have sample data. So for that reason, it's definitely not the normal distribution. We're going to use the t-distribution for this problem. The data given is a sample, and so we have access to finding its sample standard deviation. We also need the sample mean, which is not given to us here. So on our calculator, the feature that we use to get the sample mean and the sample standard deviation are 1var stats. It'll give us the sample mean and the sample standard deviation. So we have our data in a list, and then we're going to find the sample mean and the sample standard deviation. So with your calculator, you put males into L1 and females into L2. If you run 1var stats on L1, you'll get the sample mean for males. And then if you run the same 1var stats for females, you'll get the sample mean for females. After you get the sample mean, you can also take note of what the sample standard deviation is. That's the row that says SX on the calculator. So you'll find it for males, and then you'll also find it for females. And then what we're going to do is we're going to use that sample standard deviation to get the standard error. Basically, we're going to use S and divide it by the square root of n to get the standard error. So X bar for males is 74. S for males, or SX on your calculator, came out to be 13.0979. So again, you're using one var stats to get these two values. Now you're going to go to the formula. The formula for a 95% confidence interval has a t-score of t 97.5%. Okay, so that t-score goes here and here. X bar is the 74 that you got out of your calculator. S is the 13.0979. It's going to go in the numerator here. And N is 10. You're going to go to the t-distribution chart to find out what the t-score is. So you go to the column labeled T97.5, which will give us t-scores for a 95% confidence interval, and you go to the row with a degree of freedom of 9, because degrees of freedom is n minus 1. So going to your t-distribution chart, you should get a t-score of 2.26. If you need help with that, let's look. We're going to go to T97.5. We're going to go down to the degrees of freedom of 9, and it's 2.26. Okay, plugging those values into the formula, you have 74 minus 2.26 times 13.0979 divided by the square root of 10 to 74 plus 2.26 times 13.0979 divided by the square root of 10. So you go to your calculator and you plug this in and you get your answer. It should be 64.64 to 83.36. Whenever you're asked on web work to do a problem like this, you will be told how to round your answer. So I'll demonstrate it on the calculator. You're going to, where is it? Quit that screen. Okay, you've got your mean minus 2.26 times 13.0979 divided by the square root of 10. So when rounded to two decimal places, we have 64.64. And if we change that minus to a plus, scrolling over, okay, there we go. Scrolling over, changing the minus to a plus, we have 83.36. So when asked to interpret, we're going to use our standard interpretation. We are 95% confident that the true population mean pulse rate for males is from 64.64 to 83.36. So when we find the values for these confidence intervals, we always express how confident we are in our estimate. Because there is a 5% chance that we picked 10 males that were either on the far left of the bell curve or on the far, or actually this is the T curve, the far left of the T curve or the far right of the T curve, and those sample means happen to be so far away from center that the estimate doesn't hold true. So we always specify our degree of confidence. The 5% chance that we picked a bad sample is possible, and that's why we always state how confident we are in our current estimate. And again, it's easy to find the margin of error. You would find it if you wanted to by taking 83.36, subtracting 64.64, and then taking that answer and dividing it by 2 to get half of the width. We're going to do the same thing for females. So once the data is in a list on your calculator, you're going to run one var stats, and you're going to get X bar and S, the sample standard deviation. Make sure you get S and not sigma, because again, this information is a sample, not a population. So it would be wrong if you took the value for sigma. You have to take the value for S. So you should find X bar is 94.8, and you should find sigma is 14.7332. Once you get those values, you can go to the formula for a 95% confidence interval and plug in what you know. Conveniently, the t-score that we had for males is the same as the t-score that we're going to use for females, because we have the same sample size, therefore the same degree of freedom, and the same column, t subscript 97.5. So our t-score is the same. The values that are going to change are your value for the sample mean, the sample standard deviation, and n. So the t-score is 2.26 again. Plugging that in, you have 94.8, your sample mean, minus 2.26 times 14.7332 divided by the square root of n. And then change the minus to a plus, and that will give you the upper end of the confidence interval. So I could show it to you on the calculator. 94.8 minus 2.26 times 14.7332 divided by the square root of 10. So 84.27 on the low end of the confidence interval, and change the plus to a minus, minus to a plus to get the upper end of the confidence interval. $105.33. So to interpret 84.27 to 105.33, we are 95% confident that the true population mean pulse rate for females is from 84.27 to 105.33. So there's a 5% chance that we picked a sample of females that is either far to the left or far to the right on the t-distribution. And if we did, then our estimate is not good. But chances are 95% chance that we picked a sample that works, and therefore our confidence interval is valid. It means that the true population mean is somewhere in this range. So now that we have to answer the last question. Could they both be the same? Could the pulse rates for males and the pulse rate for females be the same? The mean pulse rate for all males and the mean pulse rate for all females. Could the value be the same? So here's a visual that demonstrates the confidence interval for males. It goes up to 83.36, and the confidence interval for females starts at 84.27. There's a gap in value between 83.36 and 84.27. Now that gap indicates that it's possible that the population means pulse rate for males and the population pulse rate for females are not the same or could not be the same. We know that this range is correct with 95% certainty, and we know that this range is correct with 95% certainty. So with 95% certainty, we can say that the true pulse rates for males and females are not the same. So The answer to this question is no. Since the confidence intervals for male and female pulse rates do not overlap, the population mean pulse rates cannot be the same. The female population pulse rate must be greater than the male population pulse rate. We know this with 95% certainty. So, with 95% certainty, we can say that the two population mean pulse rates are different and that the pulse rate for females must be higher. If the confidence intervals overlapped, then with 95% certainty, we could say that they could be the same. But since they don't overlap with 95% certainty, we say that they must be different.